So the last the last peripheral we're going to be, at least in labs, that we're going to be learning new throughout the labs is this thing called the eQEP. So enhanced again, QEP. Quadrature Encoder Peripheral, I'm pretty sure is what that stands for. And I don't remember one that was never enhanced. I don't remember a QEP unit that wasn't eQEP, so that's kind of funny. But anyway, so it's a Quadrature Encoder Peripheral. It's got really one job, and that is to monitor the A and B channels of a Quadrature encoder. Okay? And I'm going to explain what this idea of quadrature means. And we talked about this the last 10 minutes on Wednesday. But if you recall, there's actually a number of different ways to generate these A and B signals that are pulses that can be used to figure out the angle of some wheel. Or actually, there's a lot of linear encoders too. They put down a reflective strip, say on a gantry system that goes X, Y, and Y, X, etc. And they have this little module, and on the base is a reflective strip, and they gap that well enough so that that just goes along that that magnetic, well, not magnetic, reflective strip, and sees and doesn't see the reflection. Sees, doesn't see. Sees, doesn't see. It's always something that's making a square wave. On, off, on, off, on, off. And that's why the encoder on our motors in lab is a magnetic wheel. So there's a Hall effect, seeing magnetic fields, not seeing, seeing, not seeing, seeing, not seeing. And the whole key to this is that all those seeing, not seeing are designed to be equal distance, right? So you know, and for example, the most classical one is called an optical encoder. And it's in industry on many, many motors. And optical, so that, the problem with that reflective one is if there's dust getting on there and things like that, they can screw it up. A lot. These are encased, these optical ones, but still maybe over time there can get things in there, but for the most part not. And so what happens is this disc is etched, I'm sure it's photo etched, right? And so then, and it's photo etched so that each of these slits inside there are equal distance. And as that wheel turns, the phototransistor, this light is always on, okay? And sometimes there are two slits. It just depends on the manufacturer. You could do it with one, you could do it with two. However, these slits let light through and then don't let light through. Let light through and don't let light through. And so these two transistors are seeing on and off, on and off. Okay? There are even more complex ones. Maybe don't even think about it, but just to let you know, there are ones that also give you a sine wave. Okay? And they can get even higher resolution out of those things. They come in and they sample using some type of analog to digital conversion. They can see, even precision of the actual sine wave too to get a position. But anyway, ours are just on off. Okay? And the key to this is, and I think I talked about this a little bit last time, but they design the placement of the two phototransistors such that the square waves are 90 degrees out of phase of each other. Okay? And so let's see how well I can draw this. So this is our A signal, this is our B signal. Okay? The whole key, what we talked about last time, if we just had one square wave, that's some useful information, but it's not really enough for getting the angle of the wheel. Yes, if we knew the wheel was always spinning in the positive direction, then we could use just one pulse and count every rising edge, for example, or every rising and lowering edge, because we know the distance that's traveled from here to here. We know that's one slit, don't we? And then another slit. So if it was going in the positive direction always, you could count those edges, and that would give you an angle. All right? The count would equal the angle. The problem is if you stop or whatever, a reverse direction, you still just get a square wave out of that one channel. With this A and B pair, look what happens. We have these 4 states. So this eQEP, what it can do really well is decipher these 4 states and keep track of a count. So I'm going to just draw this, these 2 pairs, signals, have 4 states, don't they? We have the state where both of them are high, where A is low, B is high, where both of them are low, and where A is high, B is low. And then it repeats, doesn't it? Then we're back to high, high. Okay? And so what this eQEP does is it's monitoring this signal way faster than the distance between edges. So it's sampling these 2 signals at a really fast rate, and when it sees that it switches from one state, say high, high, to low, high, it knows to increment a count. And that's what its job is. When you go read it, you're going to be reading a variable called QPOS count. So quadrature position count is what that stands for. It's the register. And that count can, by the number of slits or the number of magnetic poles in your encoder, can be converted to an angle in radians. Okay? And so also, as long as it keeps on traversing in this direction, the count goes up, for example. And so high, 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 low, high, etc. Keep on going. But now if we reverse direction, what happens is the states start going backwards. And so when we go from high, high to high, low, now the eQEP decrements the count. Okay? And so this count is proportional to the angle that the encoder has turned. All right? There are some neat features, and if you're interested, there's some other things, and the lab talks about that a little bit. We're going to use this basic format for the eQEP. But there's some other neat things that the eQEP can do. For example, it can measure the amount of time between 2 edges of these square waves, and you can find velocity, in a sense, in 2 ways. And if you're interested, if that's something that sounds interesting to you, learn a little bit more about the optical encoder peripheral, that's something we could talk about for your final project. But anyway, we're going to be using the basic features of it, which is really just counting these states. I'm going from this state to this state to this state, incrementing the count, incrementing the count, incrementing the count, or decrementing if I'm going back in the other direction. Now this idea of quadrature, the quadrature encoder, quadrature optical encoder, you'll see that. That comes down to this whole thing of this times 4 states per slit, per magnetic pole of the encoder. So what happens, do you see, a slit, a full slit would be, I'm not seeing light, then I'm seeing light. Not seeing light, seeing light. So what a manufacturer of encoder would do, it'll say it's got 1,000 pulses per revolution, for example. And that's the number of little slits in the wheel. Or same thing with encoder poles. Now, notice that this full period from here to here is 1 slit. So if you have 1,000 pulses per revolution encoder, you actually get 4 times that number of counts, don't you? So that's where this quadrature comes from. We're going to find in lab that our encoder is pretty basic. These optical encoders can have 1,000 slits per revolution, really high resolution. Our little motor, again, to make it inexpensive so I can give them to you at the end of the semester, we only have 5 magnetic poles per revolution. Woo! All right? But, look nicely, we have 5 poles. That allows us to multiply that by 4, so we have 20 counts per 1 revolution of the motor. But then the other good news is that we have a 30-to-1 gear ratio before we get to the wheel. So our resolution, right, is 20 times 30 to get the resolution of our wheel per revolution, right? The number of counts per one revolution of our wheel. So that does allow us for a little bit better resolution, okay? If I was gonna, I've done this in this SegBot before with 100 count per revolution, 100 pulse per revolution encoder, and then that's, of course, then is 4,000 counts times the gear ratio of 30. That has even more resolution, doesn't it? But that's a little more expensive encoder. Okay, that encoder costs, I think, like 30 bucks, where this one that we're using is like a $7 encoder. So anyway, I think it's $7 for the pair too, I think. Well, I don't remember. Anyway, it's a much less expensive. So I was a little worried when I first played with this. I was like, oh boy, is this going to be enough resolution? Ends up being, yes, it's plenty of resolution for what we want to do. I don't know, maybe if we compared with a higher resolution, maybe you could get a little better control of the SegBot or something like that, or of your robot car. I haven't really played with that. Okay, so keep that in mind for this week when you go read that pause count, Q pause count register. All right, that is a count, an integer that you can very easily convert to radians, can't you? Because you figure out how many counts per one revolution of the wheel, and then you can convert that to radians, right? Because those number of counts equals 2 pi. And then the same thing, we could take the radius of the wheel. That's our final thing, is we want to know how fast the robot's going when it's on the ground in forward direction, for example. Okay, so we can, and we're going to convert that to feet. The only reason, I know everybody loves metric, and I do too, but the tiles on the floor in the lab are 1 foot tiles. So it's very nice, once we get the robot going at, say, 1 tile per second, you can kind of look on the floor and say, oh yeah, that makes sense. That's going about 1 tile per, so you can, if you don't like feet, because it's not metric, you can call it a tile if you want. So it's our own units. But anyway, so that's what we'll be doing for that. Okay, that clear? Good. So now, great, we've got this final feedback that we need. What have we done before? I think it was lab 3, wasn't it? Lab 3 is where we did PWM. And we have our functions, what did we call them? Something like set PWM or EPWM. Was it 2A, I believe, and 2B, which drive our DC motors, right? That drive the motors of the robot. Now I can't remember, did we find velocity back then? No, did we? No, we just moved them, didn't we? We just kind of went up and down. That's right, that's right. I get labs mixed in my head, and I have SE 420 I'm teaching this semester too. But anyway, but this, what we got to do first now, we have these functions that move the motors, okay? And you, back then in lab 3, you also figured out the polarity, what input you had to put, what sign of the input, such that both wheels went in a positive direction, right? We need that. We need that polarity correct. But now we've got our command, we can drive the motor with varying torques. Now we need our feedback. Well, we've got it in our quadrature encoder to know the angle of the wheel. But what we want to do first is we want to tell the robot car to go at a certain speed. And then we're going to see by the end, we also want it to turn at a certain turn rate too. So by the end of this lab 6, you're going to be taking your laptop and a longer USB cable, and you're going to be steering the robot car around on the floor. Okay? But to do that, we need to do a speed control algorithm. So the first thing we need to do is get speed from this position. And once I write it on the board, it's very obvious. You may need to think about it when the lab takes you through this. But how do we find speed? So, this wheel, if it's just going at a constant rate, right? Our versus time, our theta of the wheel is just going to be going up, 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 isn't it? Okay, especially if it's at a constant rate. Now, if we slow down or whatever, the curve would look a little different. Obviously, you guys all know that theta dot is this slope, isn't it? And that's what we got to find for both sides. We're going to need both sides too. We need to control both the left and the right wheel. Well, at first glance, maybe, all you're getting we're going to be sampling every 4 milliseconds. The reason for 4 is coming up in lab 7. We're actually going to sample the IMU like we've been doing every 1 millisecond. We're going to take 4 of those readings and average them together to give us a little bit cleaner acceleration and that. So what we're going to do is we're going to oversample the, actually we're going to read the encoder too. So we're going to oversample the encoder and the IMU and then take an average of those feedback readings and then update our control law every 4 milliseconds. So that's lab 7, so that's where that's kind of coming. But for lab 6 here, we're just going to sample our encoders every 4 milliseconds. So what we have, if we looked at this after we've collected all this data, right, we've got all these thetas along this line or whatever as it's going up. And so, this is a theta at time whatever. We're talking in units of sample rate, so we can think of that as an integer. We get a theta at one time and then the next time and the next time. So we think of that kind of like a theta k. This is going back to our filter stuff that we were doing in lab 4, right? So we can call this, say, theta at time 100. And this is theta at time 99. This is theta at time 98. Now, of course, if you want to convert that to seconds, it'd be 98 times our 4 milliseconds, wouldn't it? Yeah, that would be the time we're at. Well, we know that how much time is progressed between these is all 4 milliseconds, isn't it? Etc. So this is a lot of times called capital T or sometimes T sample or something like that. And so that's our sample rate. We're going to say every 4 milliseconds. So the velocity is pretty easy, isn't it? It's just what the angle is currently minus what the angle was 4 milliseconds ago divided by 4 milliseconds, isn't it? To get that slope. Because we don't know what's ahead, but we do know what was behind us, don't we? So we can say our velocity, or let's call it omega, angular velocity, is equal to theta, so we'll call that k, right? That's current time, minus theta k minus 1 divided by 4 milliseconds. Okay? Now the only confusing thing, I guess, as people look at this, what is theta k minus 1? Right? Especially that first sample. That always is a brain teaser, right? So that first sample, you go read 1 theta, that first, you get in that 4 millisecond sample timer, you go and read your theta k, time 1, I guess. What's theta at time 0? Probably 0, right? But it could be whatever initial conditions you want. So that's the place where you kind of get a little confused. In the filter code, what we did in lab 4, we just set them all to 0, didn't we? All those old states. Okay? And that's what we'll do here too. Wherever the robot starts, that's theta 0 for those motors. Because where theta is going to be important for where we are x, y, z, but not important for our velocity. Okay? And then from there on out, the key to this guy is to make it a global variable. So every 4 milliseconds, we're going to find what omega is, and then we're going to say, before we exit our 4 millisecond sample rate, sample function, we're going to say xk1, theta k1 is equal to theta k. See what I'm doing? I'm saying, okay, I know the next 4 milliseconds, I'm going to need to know what theta was at this moment in time, don't I? So I save that to a global variable so that the next time I come into my timer interrupt function, I have what theta was 4 milliseconds ago. And we're going to need that not only for calculating velocity, you're going to see in a second, we need that for calculating our integral of the error. We're going to talk about a PI control. We're going to need it in the when we get to the segue in lab 7, we're going to need to know, we're going to need to filter this velocity right here. We call this kind of a raw calculation of velocity. Pretty noisy. You're going to see in the next lab, lab 7, we're going to need to filter that just a little bit. We're not going to do a 90 tap filter, a 90 order filter. That would give us so much phase lag that the SegBot wouldn't be able to do anything with that feedback. You know, it's that feedback that would be receiving if with a 90th order filter would be 45 samples old, wouldn't it? Kind of half of that number old. So the SegBot just wouldn't be able to do anything with that, it would just fall over. So we're going to do a small filter, actually a second order filter, to filter that velocity a little better. Okay, so for that we'll need some old states. So I call these past states. So saving your past states. Most of the time with controllers it's only 1 or 2 steps back. So we don't have to do a big array of old states. Okay? And so, but again, we got to make sure they're global variables. Okay? So great, we've got velocity now. Now what we'd like to do is control our wheels to go at a certain speed. Okay? Now, to get into all the specifics of this, I'm sure a lot of you have taken some control classes. I know a lot of you have taken ME360 or in it right now and things like that. You know, if you're confused, I'd love this. I can sit down and talk to you more about controllers, but we're just going to touch on this in the next couple lectures. And if you want to learn more about control theory, you should take some more classes. What we're really focused on in this class is implementing that control law in C code. All right, that's the focus of the labs. But let's talk about it a little bit. Let's talk about control systems, block diagrams, some of these things you should have seen in other classes. If not, you know, talk to me and we can go over a little bit more. But I'm sure you're pretty familiar. I've seen before the standard block diagram. You know, a controller in the S domain, right? The Laplace domain. We talked about that a little bit, you know, Bode plots and things like that in our previous lab 4, I guess it was, yeah. And a lot of times the system you want to control we call G. So this is our controller. And this is in the continuous time, right? This S is in the continuous time. We could also write up these exact same block diagrams in the discrete domain, but they get a little messier. So usually when I'm doing block diagrams, I stick in the continuous domain and then just implement in the discrete domain. But anyway, so this is our controller, and this is our system, or a lot of times they call that the plant, the thing you're controlling. Okay? And, you know, we're right now, and this is what the control is too, we're looking at what's called a single input, single output system. SISO, you may have seen. Now, in the segue, we're going to have to switch gears a little bit, and we're going to have to do a multi-input system. All right, so we're going to actually be looking at, to control it, we're looking at our tilt rate, and the speed of the wheels. We'll need all that information to control the segue. But for our speed control right now, we're just thinking right now, we're thinking about one wheel, right? Just one wheel spinning. So we have a single output. And that output is our approximation of omega. All right? So this is our speed of the wheel. And we don't measure it directly, but we have a pretty good approximation of it, don't we? By just looking one step back, just like I said there. So we've got our omega. Now, you could, of course, well, one thing we can do is we can just give a voltage right here to our system, don't we? We've already seen that. You guys did that in lab 3. We gave a command to the motor and it spun at a certain rate, didn't it? And a lot of little toy robots out there do it exactly that way. They have just motors on, they don't have any feedback on those motors, and they kind of play around with what, and they have their, you know, the radio controlling things, and if they're going up a hill, they give it a little more throttle, don't they? to get it up that hill. They don't necessarily have feedback. It depends. I mean, a lot of them do have feedback these days, but you can build a robot car without this speed control because you do have direct. The problem is, you go up a hill and you want this to be autonomous and keep on going the same speed, that becomes a difficult task then. So we want to add feedback so that doesn't happen. Okay, so we could do that, but we want to add a controller such that we change the dynamics of the system. We change such that we give it a reference. We say, hey, I want to be going at 3 feet per second or something like that, right? For this big robot car. And just give it that command, and the controller takes over and figures out what control efforts needed to make it go at that speed. That's what we'd like, okay? Instead of our command being our joystick and commanding it, having to throttle up if it's not going the right speed. Well, in a sense, this controller is the joystick, isn't it? So we've got our reference, and then the key to control is this unity feedback, well, at least with single input, single output systems, this unity feedback that gives us an error, doesn't it? So this reference and the feedback are in a sense the same units. We're saying here the reference, I'd like to go at a certain speed. The feedback is giving us that speed. Now, of course, I just said feet per second. This is in radians per second. We'd have to convert that with the radius of the wheel and everything to give us feet per second, wouldn't we? But then that gives us an error. And the goal of the controller is so that that error goes to 0, isn't it? If that error goes to 0, then our system is going at the reference value, isn't it? Okay. And there's all sorts of talk about this. If error goes to 0, that means our system is stable. It also means, that it has 0 steady state error and all this great stuff that we talk about in control systems. Okay? Now, once we do this feedback, what is our new system? Our new system, we want to know what reference in, and then a transfer function, and omega out. All right? That's our final system, what we would call our closed loop transfer function, or a closed loop system. Well, do you recall that would be the closed loop with a unity feedback here, negative unity feedback, right? We get the following transfer function, CG over 1 plus CG. And I hope you guys have all seen that. Okay? Again, what I'm doing here, we're going to kind of just blindly use the PI control in lab. We're going to show you how to implement it, and it works beautiful. Okay? What I'm trying to show you here a little bit is why it works great, or what's the properties of this PI control. Notice how I keep on saying PI control. We could use the full PID, and I'm going to get to that, but you're going to see for speed control, the derivative would just be insanely noisy, and I'll try to explain that. And we also find that for speed control of a simple motor system, PI works very well. So we don't really need the derivative term of this PID. I'm sure you've all heard about the PID, and the PID controller, the reason it is so widely used is a lot of times you can just sit down with the system, implement a PID controller, tune those gains a little bit, and get a system working. You usually don't have to go through all the system identification. That takes a huge amount of time and all this kind of stuff. So simpler things, conveyor belts, all sorts of motorized systems out there. So many of them, even robot arms are out there that really they don't know the model perfectly or anywhere, maybe they don't spend a lot of time because they're able to hand tune the PID gains such that it works well. When I was at IBM, I was only there 2 years, but I got the opportunity to work with a gantry system that was X and Y. It was all enclosed in granite slabs and all this kind of stuff that need to be really precise. It was probing little pads on a circuit board, but more of a thermal conducting module, they called it. But anyway, I spent, I did go to a class. There was a guy that designed, there were some control engineers that designed the whole system. And so we went to this 1-week class where they kind of talked to us about the model of the system and all this. And it was good. It kind of gave those engineers a starting point for what the PID gain should be. But we got that back to IBM. You know, we bought it from a company called Anorad. We brought that back to IBM, put all our things on it, you know, all the probes, all the extra mass, and those gains needed to be tuned. And so that was one of the things they gave me the job of, and boy, was it was frustrating because, you know, a little tune here can change the long move, the short move, all this kind of stuff. But anyway, it came back to us just hand tuning things. There are some algorithms out there for what are called auto tuning that would auto tune your PID gains. Again, they probably give you a good ballpark, but you still have to do a little finagling yourself usually when you're playing around with the PID controller in industry. Anyway, so what? All right. So that's the idea. So what we're going to do is our controller here is going to be a proportional plus integral controller, and we're going to see how that works. Okay. Well, let's just remember, so let's think about our transfer functions. If you can get by with it, a proportional control is the easiest control out there, so why don't we see what happens with a proportional control? What we find is, it depends, but a lot of times proportional control does not reject disturbances, so that's an issue. But what would happen if it was just proportional control? So all we would be doing is our control effort U is equal to Kp times this error. Okay? So what we're left with is just this C equals Kp. Now our G, now there's friction and all this kind of stuff, but to model a motor to its speed, it can be modeled pretty simply, and it's close. Static friction's being ignored here. So this time constant of the motor and our K of the motor is a very basic single exponential curve step response. And that's a lot of times that's what our motor, for the most part, our two motors, if they're going at the same speed in the same direction, that's the transfer function that we could find. We could approximate our motors to that. So, or just one motor. So let's say that's our transfer function. This kind of shows us why we need a PI control. So what we do, right? So the PI control. Well, first, I'm sorry, let's just do proportional control first. So this CG over 1 plus CG, what do we get? We get Km over tau m s plus 1 divided by 1 plus that same thing. Okay. Now, of course, we multiply through by tau m s plus 1, and we're left with Kp Km over tau m s plus 1 plus Kp Km. Okay. So this is our final transfer function where output is omega, input is our reference that we want it to go to, whatever speed. It could be a step response, it could be sine wave, whatever, however you want to put in that reference. Now what do we notice? At time equals infinity, that's when s equals 0. You plug in s for 0, and that's your final value, right? It's called the final value theorem. Well, notice it's impossible for us to get 0 steady state error. We always have Kp Km over 1 plus Kp Km. Now, if we keep on jacking up the Kp, we can get pretty darn close to 0 steady state error, can't we? The question is, does our system work well with that high of a proportional gain? And again, usually it's not. It's more of a chattery system because our velocity calculation is not super smooth. It's a choppy derivative there. And so usually you can't just jack up the proportional gain and get a nice controller. Okay? So we have this idea of adding an integral term. And this would be more back in your controls class, but you know, if you give a step input to a type 0 system, that's type 0 is an open loop transfer function that has no s that can be pulled out. So there's no poles at s equals 0. That's called a type 0 system. If you give a step input to a type 0 system and close the loop, you get steady state error. So steady state is not equal to 0. Okay? But if you give a step input to a type 1 system, steady state error equals 0. Okay? Type 1 has a single pole. Well, it's not the closed loop pole, it's the open loop pole at s equals 0. Okay? And so that's why we're going to add in this integral control. Now, what we're going to do, right, again, so we got our feedback, reference, plus, that gives us our error. Now, what we're going to do with this PI control, you're going to see that I always split these two things up. And the reason I do that, actually I want to put doesn't really matter too much, but I'll put the integrator first, right? 1 over s is an integrator. Everybody know that, right? Ki. And I'm going to sum these back together. And that's going to be my u, which I apply to our system G. And then that's what feeds back. So that's our full system right there. Now, the reason I divide these two up is because we're going to talk about this probably on Wednesday. There's a problem with just an integrator called integral windup. Okay? That integrator, if error doesn't go to 0 after a little bit of time, that integral is just going to keep on getting bigger and bigger and bigger and bigger. For some reason, you're holding the wheel, there's extra friction in the wheel, for some reason it can't get to the speed you want it to. That integral builds up and up and up and up, and then finally when it gets enough to break whatever the problem is, you get this huge input, right? Because the integral is so large. So for that reason, we have to keep these two things divided so that we can fix integral windup. But in our analysis, we would have to put, if we want to close the loop of the transfer function and all this kind of stuff just to see its properties, we need to put this together in one transfer function. Well, to do that, right, this is also, you could think of Kp s over s, right? Just the s's divide, don't they? Laplace. So we get that Kp s plus Ki over s. This is the single transfer function of our PI control. Do you agree with that? So now if we use that to close the loop, find our closed loop transfer function, right? We've got that now our C is equal to Kps plus Ki all over s. And our plant, again, let's just use that same one, Km tau ms plus 1, right? Well, we close the loop and we get Kps plus Ki all over s times Km tau ms plus 1 over 1 plus that same thing. So let's put it together down here. Km Kps plus Km Ki all over tau ms squared plus s. Right? See what I did there? Okay. Now to get this one, a nice denominator here, we multiply the top and bottom by this, don't we? And we get Kp Kms plus Ki Km all over, come on up, there we go, tau ms squared plus, let's see here, Km Kp plus 1 s plus Km Ki. Agree with that? I think I did the math right. Now look what happens to this system. This new closed loop system, at time equals infinity, s goes to 0, doesn't it? We substitute s 0 for s, and we've got a gain of 1. don't we? So that means that at time equals infinity, steady state error is equal to 0, isn't it? We get given a step input of 1, we're going to get to 1, in other words, okay, with this transfer function. And so, you know, that goes back to that whole type. The open loop system was just this right here, and see how the open loop system has a S that can be pulled out of the transfer function, left alone. They call it, so we call this a type 1 system, and a type 1 system given a step has 0 steady state error. Okay? So that's why we needed to add that integral to get ourselves a nice response. Oh well, a response without steady state error. Now our job, right? Now our job, this is identified, that's given, that's the system given. What we need to do is we need to adjust the proportional gain and the integral gain. In lab, I'm going to give you a starting set of gains, and then you're going to tweak the integral gain just to see how increasing the integral gain gives you a little faster response. So we're not going to play a lot though with tuning. When you get to the segbot, we may, depending on how well your system balances, especially if you go and use the segbot for the end the semester project, you're going to want to tune those. There are 3 gains that are in the controller for the segbot that we'll have to get into later. And you'll be adjusting those slightly to make your system work best. The gains that I have, again, are ones that I just played around with really quickly, and I'll be asking you to tune those a little bit more. For the PID, it's pretty straightforward what it needs to be, so there's not a lot of tuning involved with this one. Okay? So there we go. So in a sense, all I'm just trying to show you here is why are we using a PI control, is what I tried to show there. Instead of just saying we're going to use it, I wanted to give a little reason why. Okay? And so I got 1 minute here. So what we're going to do, right, now we want to take this guy and implement it, don't we? Well, if we think about that, we have all the feedback, right? We need error. Error is just simply what omega is currently minus, sorry. No, that's not error, Dan. What am I thinking? I'm thinking of the velocity. Error is equal to where we want to be, our reference, what speed, minus what we currently just measured. So that's really easy to calculate in our C code, isn't it? Okay? So then all we're left with is finding our integral, because we just take the integral times ki. Well, that's, you know, we say that's in Laplace, it's this. But all we need to do is implement some integration rule. So if we want to know what an integral is, why don't we use, we're going to use the trapezoidal rule. So if we think about that, you know, we can call this ik minus 1. We want to know what, now our current, this is what the integral was 4 milliseconds ago. What's the new integral? Well, this is error at time k. We'll do this again next time. Error at k minus 1. That's a minus. So what's ik? Ik is simply equal to what the integral was 4 milliseconds ago, plus this little sliver, right? You can do this in MATLAB with what's called the trap z function. I don't know if you've ever used that. But plus what? Error at time k, plus error at time k minus 1, divided by 2. That's the 2 heights of the trapezoid, isn't it? Times our sample period, 4 milliseconds. And there you go. You have just implemented the integral. And so then it's simple. Your u is equal to kp times that error plus ki times this ik. And that's what we're going to implement for our speed control. And then we'll talk about, we have to fix integral windup and a couple other things. Okay, went 1 minute over, sorry.